Okay, so welcome back. And now I will, during the last 20 minutes, I will show you the remainder of what was left on the last lecture. I'm sorry, it was supposed to be in the beginning of the lecture, but my internet provider decided to make a 15 minutes break. Yeah, it appeared exactly at the beginning of the lecture. So the one theorem, the one lemma, and the one application that was left after the previous lecture was the application to so-called Baker's technique. In bounded in planar graphs, and the key point of this technique is the following lemma: that if you've got a planar graph that is connected and has small radius, yeah, so radius at most d. So recall that the radius of a graph is a graph has radius d if I can find a vertex such that every other vertex is at a distance at most d from it. Yeah? So if I have a connected planar graph of small radius, at most d, then actually it's true if it's bounded by a function of d, even a linear function of d. So it is at most 3 times d. And sort of the intuition behind this theorem is reasonable because, well, if I have a graph of radius d, I could intuitively like fix one path here, yes, and then sort of say that I put d cops on this path if I play the cops and robber game, and then I put d cops on another path like that, and then I scan the whole graph radially, say clockwise or anti-clockwise, while restricting the area for the robber. This is a very wrong picture in a sense, and probably you will see at the tutorials why it is a very wrong picture. However, the intuition is like that if I've got a planar graph of bounded radius, then sort of putting the cops radially and searching for the robber is the right way to go to construct a small with tree decomposition. Okay, so let's just prove this this theorem, this lemma. So first of all, we can assume that the graph is triangulated. So whenever we've got a face of my graph, say pentagon face, then I can always add some additional edges to my graph in order to make this face in order to cut this face into triangles. Why so? Because adding additional edges to triangulate faces can only decrease the radius and can only increase the tree width. So if I prove this for triangulated graphs, this is even harder than for any graphs. Yeah? So if I take any graph, I triangulated, the task of proving this theorem in the triangulated version is even harder than in the original. Good. So once I triangulated the graph, I do the following. So let me fix some center vertex u. This is the vertex from which everybody is at distance d. And let me fix some BFS spanning tree from it. Maybe on this picture, this BFS spanning tree is not really a BFS tree. However, the only thing I care about is that this is a spanning tree of the graph of depth at most d. Yes, and it is rooted at this vertex u. So if the radius is bounded by d, then I have such a BFS spanning tree. So here the spanning tree edges are black, the other edges are gray. So now the key trick is to look at this picture and find another tree. And this another tree is called the co-tree, and it's defined like that. I put a vertex at every face of my graph. Observe that on this picture, I did not triangulate the outer face. The outer face is a regular face, and I could also triangulate it, but in order not to mess up the picture, I did not triangulate it. It should be triangulated as well. So I put a vertex at every face of my graph. So this tree will be formally a spanning tree of the dual graph. And what I do, I now connect these vertices inside the faces by edges that are dual to those ones that were not in the original treaty. Yeah, so here is an edge to the outer face. Yes. Here I put edges like that. Here I put edges like that. And so on. Yeah. So here, all those edges sticking out, they actually all go to the same vertex, which is the vertex outer face. Yeah. So imagine that all those vertices here are actually fused into one vertex. Yeah. So now we've got two trees on the picture that are somehow interleaving. One tree is the original tree T, that was the BFS spanning tree of the graph. And second is this co-tree, the blue one, call it S, and they are somehow interleaving. And in particular, they do not cross. So let's formally prove that this co-tree is actually a tree. So first of all, I cannot have a cycle in this code tree. Why so? Because if I had a cycle in my blue graph, in my blue tree, among the blue edges of S, then I would have some part of the black tree inside and some part of the black tree outside, right? But the black tree was connected, and the black tree and the blue edges, they do not cross. So then this would certify by planarity that the black tree was not connected. Second, I already know that my S is acyclic, so it can be a forest. So I now need to prove that it is actually a tree. And I will do it by just counting the number of edges in my S. So how many edges I do have? Well, the number of edges in my S is equal to the number of edges of the whole graph minus the edges of the tree T, because well, I took all the edges of my graph and I drew all the dual edges to the edges of the that are not participating in T. And so the number of edges of the whole graph is, say, E. How many edges does T have? Well, it is a tree, yes, with say V vertices. This is the number of vertices of the graph, and a tree on V vertices has V minus 1 edges. So the number of edges of S, yes, is equal to E minus V plus 1, which by Euler's formula is equal to the number of faces of the graph minus 1. And well, now I see that S is a forest with how many edges? With the number of edges being equal to the number of vertices of this forest minus 1. So if a forest has one less number of vertices, number of edges than the number of vertices, it must be a tree, it must be connected. So indeed, we have proven this fact that S is, this co-tree is indeed a tree. So now when we understood that this blue tree S is indeed a tree, we can define a tree decomposition of our graph. Our tree decomposition will have this co-tree S as the template, as the tree in which we embed and with which we associate bags. And the bags are defined as follows. So recall now that all the faces are triangular. So let me pick some interesting face here. Maybe this face is interesting. Yeah. So now I need to associate the bags with faces of my graph, which are vertices of my co-tree. Yeah. So with each face, recall, is a triangle. So it has 3 endpoints. And I associate the union of vertex sets on the paths from the corners of this triangle, from the vertex of this triangle to the vertex U. So I take this path in my tree T from the corner of from the vertex of the triangle. I take all those 3 paths, yes, and all the vertices that appear on those paths, they are included in the bag of associated with my triangle. Yeah. So this is this definition. So now observe that here I've got at most D plus 1 vertices. Here I've got at most D plus 1 vertices, and here I've got at most D plus 1 vertices, because the depth of my tree T was at most D. So every path from even a leaf to the root has at most D plus 1 vertices. So all in all, the size of this bag B of X, Y, Z is at most, well, 3D plus 3 I would write by brute force, but all of those paths share the same vertex U. So it's actually plus 1. So indeed, the bags are of size 3D plus 1, which gives you a tree with at most 3D. So the only thing that remains to argue, and I will not do it fully formally because this will be easily seen from the picture somehow, is that this is indeed a tree decomposition.
Excuse me, can you repeat how we are defining our decomposition? I did not get it.
Yeah. So the base tree of our decomposition is the tree S. Is this clear how the tree S is defined?
Yeah.
So now how I do it, now I need, with every vertex of the tree S, I need to associate a bag. What is a vertex of a tree S? A vertex of a tree S is a face of original graph.
Yeah, with
this vertex
here.
here. I take 3 vertices that are on this face, the 3 vertices of this face, and I take the paths inside the tree T to the root U.
From each vertex.
Yeah. So X, Y, Z are the 3 vertices of my face of interest. Yes. And then I take the path from X to U, the path from Y to U, and the path from Z to U.
Okay.
And I take the union of their vertices.
Okay. And what happens with the outer face?
The same. The outer face is the same story. The outer face is a triangle, I recall. I did not draw it as a triangle on this picture, but the outer face should be also triangulated.
We want it to be a triangle. Cool.
Yeah, actually, there is no outer face. I can always think of embedding the graph in a sphere, and then all the faces are bounded. Good. So now the only thing that remains to argue is that whenever I take a vertex, well, it is clear that every edge is in some back, because every edge participates in some triangle, and then the back associated with this triangle contains this edge. The only thing that remains to argue is that whenever I take a vertex, the set of backs that contain this vertex, they form a connected subtree of S. So let's see, for instance, for this vertex, which guys contain this one. Well, this vertex, maybe I will take a different one. Maybe some more interesting vertex, maybe this one. Okay, let me look at this vertex, say the red one. I would like to understand in which backs this vertex is contained. Well, he is definitely contained for every vertex that is somehow below him in the tree, that is shielded by him in the tree from you. Yes, he is on the path from this vertex to you. Yes, so all these vertices, so all the triangle faces that are incident to the vertices that I just drew in red, they will contain this vertex of interest, this one. So which are those faces? This one, this one, this one, this one, this one. Well, outer face, this one, 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 and this one, right? So all the faces that are incident to this subtree. That is the subtree that is rooted at the vertex that I'm interested in. So now observe that in the tree S, these faces are connected. Why? Because I can move somehow. I can now start with here and move around, make a tour around this red subtree. Yes, going through faces, and every 2 faces that are visited by this tour are connected by an edge. So all of them will create a connected subtree of my cotree S. Good. So I have now just checked that whenever I look at a vertex and I look at the bags that contain this vertex, they form a connected subtree of S, because I can make this tour around the subtree rooted in this vertex, the subtree of T. Good. So is this clear? Maybe some +1s to make it more.
Can you explain again a little more, maybe, I don't know, why that subtree is connected? Why we can take the tour? How do we construct
so
the tour?
maybe I will draw it. So here is my vertex U, somewhere there. Here is my vertex of interest, say call it V. And here is my subtree rooted, this is the subtree of T rooted at V. Right? So now V will is in the path is contained in the node to root paths for all the vertices of the subtree. So V will be contained in all the bags associated with the triangular faces that are incident to the red vertices. And now I need to prove that they form a connected subtree of S. Why so? Because I can take this edge here from V to its parent. Here are two triangles. And now I can go around the red subtree in the plane, following closely this red subtree. And in this way, I visit consecutive faces of my graph. And every time I'm going from one face to another face, I'm going through an edge that is an edge in S. So in this way, I create a connected tour that visits all the faces that are incident to the red subtree. So all those faces need to be connected in S. Is this clearer?
A little bit. I'm still not entirely sure why that path is never broken by T.
Well, because T is a tree, right? So yeah,
so
imagine that I follow. Imagine that I follow the edge.
We're already considering.
Sorry, can you repeat?
Mm-hmm.
Imagine that I follow the
yeah. So it's like if there like any.
So if I start from here, I really go closely next to this subtree. So my tour that I am now drawing in the plane, it will never actually cross the edges of T, because I am going only through faces, and through edges. I may be crossing some edges, but these are edges that are not participating in T because I'm going around T.
Okay, that makes sense. Thank you.
Yeah. Good. So let me now give you the application of this, a very quickly application to a problem. This is the subgraph isomorphism problem. And the subgraph isomorphism problem is a very simple problem. I'm given two graphs, the pattern graph H, pattern, and the host graph G, host. Yeah. And I just ask whether H is contained in as a subgraph in G. Yes, so I've got some large graph G, and I ask whether I can find here some copy of H somewhere there as a subgraph. Yeah, so this is a very, very basic problem, and we consider it as a parameterized problem where the number of vertices of H is a parameter. Yeah, so we are really thinking of trying to find a small pattern H in a large graph G. So as we will see in general, this problem is quite intractable because it in particular encompasses the clique problem if H is a clique, so checking whether there is a complete graph on P vertices. However, in planar graph, it is FPT. And the running time that we will get, it will be roughly P power P times linear in L. And for the purpose of this talk, we will assume that the host graph is connected. If it's not connected, you need to treat every connected component separately and do some dynamic programming on connected components of H. It's easy and boring, and therefore we'll assume that H is connected. Good. So how do we do it? So first of all, let me fix some solution. Yeah. So here is my subgraph H0 somewhere there. Yes. Maybe on 4 vertices. That is there somewhere in my graph. Okay, maybe I will not draw it so far here. So I have some subgraph isomorphic to H in my graph. Then I pick any vertex U and I run BFS from U. Yeah, and the consecutive layers of the BFS are L0, L1, L2, L3, and so on. So the if layer consists of all the vertices at distance exactly I from U. So then my H0 is somewhere there. Yeah, maybe it is drawn somehow like that. But the idea is that H0 has only the number of vertices of H0 is at most P. So it can affect only P layers. So the observation is that if I now order consider all the layers modulo p plus 1. So with every layer, I associate its remainder modulo p plus 1. So this is a number from 0 up to p. Then there is one modulus, one remainder a, that is not affected at all by h0. Yeah. So for instance, if I have here now p is equal to 4, yes, the modulus looking like that, then this one, yes, then 4, 3, then this one, and so on. These layers will not be affected at all by h0. So if I delete them, h0 will still be there, right? So what my algorithm does is it does this layering and it guesses the remainder a, yeah, by trying all possibilities, and these are only p plus 1 possibilities. Yes, I'm guessing this remainder a such that layers congruent to a modulo p plus 1 do not contain any vertex from my solution. And I just remove them, yeah, because now I know if I guessed correctly, I know that by removing those layers, I cannot break the existence of a solution. So now comes the crucial claim. The crucial claim is that after removing those layers, every p plus 1 layer, the tree-width of the resulting graph is bounded by 3 times p plus 1. Yeah? So how the graph actually looks like? It looks like here on the picture. You've got you are making the consecutive layers. You can sort of think of them as those rings. This is not entirely true, but let's think for now on the intuitive level in this manner. And now we need to show that this graph has bounded truth. Now, between every consecutive rings, so a ring is just a batch of p consecutive layers with the same and not having this remainder a modulo p plus 1. Yes, these layers are entirely separated from these layers by this layer, by the layer that I removed. Yeah, because I made a BFS layering. So by BFS in a BFS layering, the edges can only be within one layer or between two consecutive layers. So now, after removal of those layers that I removed, my graph disconnects into several connected components, and each connected component is contained exactly in one of those rings. And each of these rings has width p, has width at most p. So now, in order to prove that the tree-width is bounded, it suffices to prove that the tree-width is bounded in each ring separately, so that every p consecutive layers, they form a graph of bounded tree-width. So this already looks very similar to what we did before. But now I'm looking at p consecutive layers, not necessarily the p consecutive layers that are very close to u. So how to prove that this graph is bounded tree-width? So first of all, let me do the following surgery on this graph in order to convince you that the tree-width is bounded. Let me remove all the stuff that is outside of this layer. Yes. So this is, I'm doing a surgery on the original graph. I'm removing all of the stuff that is outside of this thing. And I'm looking at all the vertices that are inside. So these are the vertices whose distance from u is smaller than the distance of the guys from this layer. And they form like a prefix of the BFS tree, the top part of the BFS tree. And this top part must be connected because for every vertex, there is a path in the BFS tree going to the root. So because this is connected, I can contract all of this. Well, maybe this was not the best color. I can now contract this whole part onto vertex u. So I now made two operations in my graph. I removed the stuff outside, and I contracted the whole part inside onto one vertex, onto the middle vertex. And the ring stayed intact. But now, after contracting this middle part into this single vertex, the graph has radius at most p plus 1. Yeah, because now everybody inside this ring is at a distance p, is a distance at most p plus 1 from the part that got contracted onto the middle. Yeah, so now it is a distance at most p plus 1 from the middle vertex after the contraction. So then after the contraction and removing outside and contracting the inside, I've got a graph of radius at most p+1, which by my lemma has radius, has true at most 3 times p+1. So now to say that the ring itself has a radius at most, has true at most 3 times p+1, well, I now prove that a supergraph of this graph has a true at most 3 times p+1. The supergraph obtained from this graph by adding this, this point in the middle, the contraction. So now that I see that tree-width of my graph after removing the layers is bounded, I can run a dynamic programming for my problem. And this dynamic programming, if you think about it, it runs in time as roughly W, the width times to the power order of P. I will not give, let me leave it as an exercise. It's a technical check that you can indeed make such an dynamic programming. Now, W is something like 3P or 3P plus 3. Yes. So all in all, I can now run dynamic programming for every possible choice of A to check whether for any choice of A, I was indeed able to find my a subgraph isomorphic to H. Yeah. So to summarize, we are going through all the possible remainers modulo A. For each remainder modulo A, we are running a dynamic programming algorithm on a graph of bounded tree-width. And we have a guarantee that if there was a solution, then for at least one choice of A, the solution will be found. Good. So this is called Baker's technique. Originally, it was designed for approximation schemes in planar graphs. You will see it actually during the tutorial, I guess. However, it is also a parameterized technique, and it is powerful for various sort of local problems where you can localize the problem to a ball or several balls of small radius around some vertices of the graph. Good. Are there any questions to this technique? Should I clarify something in this proof? Okay. If not, then thank you very much for today.